Our speaker tonight is Dr. Roger Wiens. Roger Wiens holds degrees from Wheaton College and the University of Minnesota. He wrote the first thesis on the composition of the Mars atmosphere measured in the laboratory, sourced from Martian meteorites. He was a developer and flight payload lead of NASA's Genesis cosmochemistry mission. Subsequently, he developed and led exploration with the ChemCam laser remote sensing instrument for the Curiosity rover, which landed in 2012, and he now leads the SuperCam instrument team on the Perseverance rover, which landed in 2021. With its international team, SuperCam uses 3 spectroscopy techniques, a microphone, and high-resolution imaging to study remote targets. Dr. Wiens is a senior fellow of Los Alamos National Laboratory, where he developed these instruments. As of 2022, he is a professor of planetary science at Purdue University. He's been knighted by the government of France for forging strong ties between the French and American scientific communities and for inspiring many young, ambitious Earthlings. Please join me in welcoming Dr. Wiens.
I wanted to start with this just to give praise to the Lord. So it says, "Praise the Lord, I will extol the Lord with all my heart in the council of the upright and in the assembly, which we are. Great are the works of the Lord, they are pondered by all who delight in them. Glorious and majestic are his deeds, and his righteousness endures forever. He has caused his wonders to be remembered." And so it's great to be able to meditate on what God has done as we look at part of the universe. And so I'm giving thanks, first of all to God. I want to also recognize my family. This was a recent picture. The 2 boys are on either end. And if you read my book, you will hear the little child voices of these as they were young children, as I was building the ChemCam instrument. And they were wondering why I was having so much trouble making this instrument work. And you can hear their sarcastic voices as they got to be young preteen kids. But anyway, they supported me through all that, and so did my wife. And now we have a lovely daughter-in-law as well. So that's them. Here is the team, the science team of the ChemCam instrument. And as the team is half French, half of the instrument is contributed by the French Space Agency. We're sitting there on the rooftop of the Paris Observatory back in 2013, just around the time of the landing of Curiosity. This is the SuperCam team, and this picture was taken at Caltech last summer. And so this is many of the people on that team. And so it's really grown. We have a lot of different techniques that we're using on SuperCam. And it's just been so fun to be part of these Mars exploration teams, let alone be the leader of this. And so I just thank God so much for what he has done. I did have this previous space mission that was called Genesis. And then basically when I got to Los Alamos National Lab 25 years ago, there was a guy who had this technique who was interested in getting it proposed to NASA, and we worked on that, and it was successful. And so Los Alamos is the place that I lived and worked to build these instruments in collaboration with the French Space Agency. So here I am before leaving Los Alamos, looking through a plexiglass window at the flight units of our SuperCam instrument, and I'll explain those in just a little bit. The main technique that both ChemCam and SuperCam use is called laser-induced breakdown spectroscopy, or LIBS. And we take a pulsed laser beam, and it's only 5 nanoseconds long, and it's about 12 millijoules. We focus it down to a spot the size of a pinhead, basically about 200 to 400 microns, at a target that's somewhere between 2 and 7 meters away from the rover. We've actually been successful up to 11 meters away, so that's about 35 feet. And And then we fire this laser, it creates a small flash, and you can see the different colors down below. I'll show you a video in just a minute. And we collect that light with an optical spectrograph and get the wavelengths of that light, which tells us the elemental composition of the targets that we've just shot. The other nice thing is that there is a shock wave involved. It creates a sound, which tells you why we have a microphone on SuperCam. And it also has a small shock wave that blows the dust off. And back in 2004, when we first proposed this technique, NASA was finding that their remote sensing techniques from the rovers were having a hard time because all the rocks were covered by dust. And so this is a nice way of having a super long arm that's 25 feet long that reaches out and just brushes the sample off, and then we get the analysis. So it's worked really well in that sense. So ChemCam, this is the mainstay of it, and we also do imaging with ChemCam. And in SuperCam, we can clear off the dust, and then we can use several other techniques as well. And this just shows a demonstration that was done back in the early 2000s using a backpack version that was built for the International Atomic Energy Agency. And in that case, it was a small laser that was mounted just down at the ground, an optical fiber that was set to collect that light, and then the optical fiber runs all the way up my friend Sam Clegg's arm into a backpack where the spectrometers are. So you can do this in a little bit of a distributed mode for different parts of the instrument. And that's what we did with ChemCam and with SuperCam. So here's a short video that just shows first an animation and part of the instruments. So this just shows that the rovers are both kind of point, focus, and shoot techniques from the top of the rover for both ChemCam and SuperCam. This is the optical sensing part with 3 optical spectrometers, and they're fed by optical fibers. You can see these white fibers right there. And that comes all the way into the body of the rover from the mast. Here's the top part with the laser. It was that little cylinder on the left. And then this is the telescope. It's a 4.5-inch telescope. It's the largest optic on the surface of Mars. And it has an automatic focus to it, which is happening right here. And then we'll fire at an iron pyrite target that's about 6 feet away. And so you'll see the flashes from the libs, but you won't see the laser beam. It's an invisible laser beam. So there it is. And it's actually oxidizing the surface a little bit, getting a dark ring, and it makes that bright plasma. So there were a lot of people back in the early 2000s when this first launched back in 2012 that were wondering, what does this really do? Does it, when we said it zaps rocks on Mars, but this was a nuclear lab. So the media kind of played this up a little bit. And so at the time of landing back in 2012, we got this picture on the internet trying to figure out that we don't do environmental damage on Mars. So in fact, this is what we see from those little flashes. And this is the optical spectrum with the wavelength in nanometers. Our eyes see most of the middle part of this spectrum, not quite as far into the UV or the near infrared as these spectra go. But we get all of these elements that you see labeled and many more. We know where they are. We know what they are by the position, by their wavelengths. And then we calibrate them against known standards, and we get these elemental compositions. So ChemCam was the first instrument to use this technique on another planet. This is actually the very first spectrum we got from Mars, shown here. Since then, we now have this on SuperCam, but the Chinese also decided this was a great instrument, and they developed their own version, and it's called Mars Code on the Tianwen 1 rover mission that is on Mars as well. So there are now 3 LIBS instruments on Mars, 2 French US instruments and 1 Chinese. So let's talk a little bit about Mars and why are we studying Mars? What can we learn about God's creation from Mars as compared to Earth? Well, you know that Mars is the next planet in the solar system, so it's a little farther from the sun, gets less sunlight. But a really important fact is that it's only 1/10 of the mass of Earth. And that's really important because it has less gravity, has only 38% of Earth's gravity at the surfaces of the respective planets. And it doesn't have a magnetic field. And so over time, Mars, because of that smaller size, lost its almost all of its atmosphere. It now has an atmosphere that's only 1% as thick as the Earth's. And so the fact that it doesn't have clouds and a blue ocean is really a result of that loss of its atmosphere, which is a result of the fact that it's a smaller planet. And that speaks very much to some of these factors and parameters that Hugh Ross and others talk about so much, which is that we have life and intelligent life on Earth due to the fact that it is hospitable. But Mars was once hospitable long time ago before it lost its atmosphere. And so our question and our quest in studying Mars is, was Mars ever habitable? Was it ever like this? And we see two things in this, or three things. One is there's an atmosphere, so there's haze on the horizon. Two, there's a big ocean. And then third, there's some green areas in this. Now there was almost, we know for sure that there was not photosynthesis on Mars. There was not this chlorophyll, not the green material that we have on Earth. But we'll talk a little bit about when that developed on Earth as well, and what we're looking for on Mars as well. But the real question was, how habitable was Mars, and did it ever have any forms of life, single cellular forms of life? And even if you believe that that God would have created life only once, and we're the product of that here on Earth, even in that case, we might expect to find life on Mars. That's because we've had interplanetary travelers in the form of meteorites. This rock that I'm showing here is a meteorite that I was studying for my PhD thesis back in the previous millennium. This rock experienced a lot of shock, physical shock. And so it has all these cracks running through it. And at one time it had little, we think it had little holes or vesicles or vugs. And where you see those gray areas, those were actually filled in by glass when it had this tremendous shock. And in fact, this one here near the bottom, you see a crack all the way around it. So in my PhD thesis, I was studying the gases that we could measure coming out of the glassy areas that we think were once open spaces there that were holding a small amount of gas. And what we found were gases from the Mars atmosphere. And that really proved to us that these rocks were once part of Mars, but there must have been a tremendous impact at some point in the past. And these rocks flew out into space, became interplanetary travelers and traveled to Earth. But you can imagine that the converse must have happened over geologic time as well. And as Earth has had life on it for a long time, at least in the form of bacteria, any impacts on Earth that would have launched rocks out into interplanetary space would have very likely had some cellular life on board, and could have brought this to Mars and seeded life on Mars. And so we might expect to find Mars in either case, either if God formed life on Mars at some point in the past, or if God only formed life on Earth, but that it traveled to Mars. And so we're looking for life on Mars. Another really important fact about Mars is that the age of the surface of Mars, in contrast to Earth, is very ancient. On the Earth, we have plate tectonics, which is another important aspect for life in many ways, but it means that the surface of the Earth is really geologically young. Finding material that's much older than 100 million years or 400 million years is very unusual for the surface of the Earth. There are some places, of course, but on Mars, it's very different. And nearly the entire southern hemisphere is very ancient. And the northern hemisphere is really also very ancient by Earth standards, most of it being almost 3 billion years old. And it's only the Tharsis Bulge, where we have the largest volcanoes on Mars, and in the northern and southern polar regions that are younger. Now, if we look at what was happening on Earth at similar times, the very earliest forms that we recognize of life on Earth are about 3.5 billion years old. And but there's very, very few places on Earth that we can go that really have rocks that are that old, that have preserved this. And so if we go to Mars, we can find that everywhere, that age of those rocks. And so the question is whether we would find very primitive life on Mars. Of course, we're still looking for that and haven't found that, but I'll explain about how we're looking in more depth, in more detail for that. So that's very important, this ancient aspect of Mars's surface when we look at Mars. Now, when we look for life on Mars, I think I mentioned already that it's really single cellular. So we're not looking for fossils like we see on the left-hand side of this slide, which is fossils that on Earth timescales just happened in the last 650 million years. We're looking for these microbial mats that have been frozen in the rock record going back to about 3.7 billion years. And I was really privileged to be able to take a trip to the Outback in Australia, sponsored by NASA, to look at Earth's most ancient life forms in the field and as the way they look. And we saw things just like this. In fact, I'm not sure that if that's my finger or not. I don't think so, but I was there and got to see these amazing features from our very ancient past. So now taking you to the technology that we're working on Mars. This is the Curiosity rover. It's the first of the 1-ton class of rovers on Mars. The previous ones were less than half the size of this. These rovers are about the size of a small car. Some people even say a small SUV. And the Curiosity rover that landed in 2012 had 10 different instruments on it. My favorite, of course, is ChemCam, which is firing the laser. But the two up there on the mast of the rover are remote sensing. So we had stereo cameras called mast cam, and in the big Cyclops eye that we call ChemCam. On the arm of the rover, we have contact instruments that really work by just with the arm moving them right up against the rocks. And Molly is basically a hand lens. The idea is that you get a view like you would get with a magnifying glass, which a field geologist would take with him into the field. And then APXS gives elemental chemistry to complement the ChemCam instrument. And then inside the rover, there are two instruments, one called SAM and one called ChemIn, that provide, with ChemIn, quantitative mineral compositions. And then SAM gives isotopic ratios and looks for organic materials, and that is carbon, hydrogen, oxygen bonds. And then there's a few other instruments looking at the radiation, the weather, and so on that are on board this rover. And this rover landed in 2012 in Gale Crater, which is just 4 degrees south of the equator. And this crater is 90 miles in diameter. It's the deepest crater for 1,000 kilometers, or about 600 miles all around. And so looking for a place where there was long-lasting water on Mars, this would be one of the best places to go. And that's why we did. You could see a big channel coming in from the south in the upper part of this picture. And then there's this large mound in the middle that from orbit looked as if it was actually sedimentary material, maybe windblown material that had filled that in. And so the mission was really to go down into the low part of the crater, look for evidence of a lake, and then start to drive up into this mound to see if we could see a transition in Mars climate, perhaps going from a warmer and wetter place that had a thicker atmosphere to one that started to dry out over time. And so this mission has been on Mars now for 10 years, going on 11. It landed in the low part of the crater, right there at Bradbury Landing, and then made several stops along the way, started heading towards the slopes of Mount Sharp, because that's where we saw the greatest evidence of clay minerals. But in fact, where we saw the greatest evidence of clay minerals from orbit, that is. But in fact, the rover actually found a lot of clay minerals in the lower part of the crater, which isn't surprising, of course, if this really was a long-lasting lake. And we found I would say, hundreds of thousands of sedimentary layers that were deposited in this ancient lake, just telling us that it was a long-lasting lake. Now, Curiosity is still exploring Gale Crater. I had to turn my attention away from it. I turned the leadership of ChemCam over to a colleague 2 years ago as Perseverance was landing. But the traverse of Curiosity continued on up Mount Sharp in 2018, crossing the ridge, getting to this clay unit, and then transitioning into a more sulfate-rich unit. And Curiosity is up in this sort of valley area right now, exploring this valley and getting up above what we thought there were the last of the lake bed layers. But we're still finding things with this rover, and it's really quite exciting. This is an overhead view, and you see this really clear valley heading downhill. It's fairly steep, actually, and then it looks like there's material that's deposited near the bottom of this valley right there. It could have been the last dregs of some catastrophic outflow that came down there. So this rover just has been exploring a place called Marker Band Valley, and that's in this overall valley. But you can see a change of material kind of heading off into the horizon, different areas. It's just below where the rover is here now, goes around over there, and then it heads off to the right. And that is a marker band. That's a geologic term that we use on Earth for a change in the strata or the late rock layering that is visible over a large or long distance. In fact, we can see that marker band around most of Mount Sharp, many miles to the south, for example. And so there were papers written about this marker band already back in 2010, years before the landing. And we're exploring that, but it probably represented a hiatus or change in the depositional history of these sedimentary rocks. But we still have seen evidence of water or probably fluvial or perhaps rainfall at times in these parts, even though we think we're above the main part of the lake bed. So there's some mysteries that the rover team is still working on solving here. And a lot of interesting, the most beautiful scenery of all of Mars, and I could say really almost the most beautiful scenery in the solar system, except for, of course, the green, lush vegetation of the Earth. So this is sort of a summary of Curiosity's major discoveries. It was a large lake in the past, long-lasting. We suspect water there for 1 million years. Maybe it was somewhat periodic. We don't know that for sure. The conditions were habitable with, at least for a long part of that time, neutral fluid conditions and not too saline. We've also found the elements that comprise the building blocks of life. And the SAM instrument also measured methane in the atmosphere today. None of these things say that there was life living on Mars, but it's a bit tantalizing. And so we're going to continue the exploration as I'll talk about with the Perseverance rover. So this slide shows the twin nature of these two rovers, with Curiosity on the left and Perseverance on the right. And they were really built with the same blueprint. They both have RTG or radiothermal nuclear power supplies on the back, and they're just really overall fairly similar in design, but they hold quite different payloads. For the most part, I'm the only person who is leading an instrument on both missions. And so you can see the similarity of ChemCam and SuperCam's boxes at the top. We did that through a very competitive process in both cases, and I just thank God that we were chosen a second time around. It seemed highly unlikely, but it's a real blessing. So there's 7 instruments on Perseverance, and I'll walk you through them in just a minute. This was the blueprint for the rover, you could say, back in 2012 when NASA announced they would do another rover. They assembled a science definition team to tell them what should be done with a new rover. And that science definition team said that the remote sensing instrument that would sit inside the box that's up at the top should study mineralogy, whereas ChemCam studies chemistry. And this committee, of course, there's always politics involved, and maybe they thought they had gotten rid of ChemCam, and they would get their own instruments on board this next rover. But we did something. I really didn't want to propose to this mission. I was having so much fun exploring Mars with Curiosity and ChemCam. But it was a time when I really felt God was really telling me something, and it was that I should propose for one more mission. And so we proposed this. This is the cover of the proposal submitted in 2014 called SuperCam. The name is maybe a little bit lame, but we wanted to convey that this is a ChemCam-like instrument, but it has been souped up. And so we added two mineral detection techniques to ChemCam. In basically the same chassis. And so now we've added a remote Raman spectroscopy, and then also visible and infrared reflectance spectroscopy, which uses sunlight and basically uses infrared vision to look for mineral compositions, especially clay minerals. We changed to color imaging, and we added a microphone as well. So it was really, NASA called it a Swiss Army knife of instruments when it was selected. It was a gamble on our part to propose this many things in one package. So it was selected, and so I was working on both developing this instrument and exploring Mars at the same time for the next 7 years, and it was a really busy time. So this shows a little bit of a montage of what SuperCam does. So I showed you the flashes from the libs, as you see in the lower left. The laser gets its frequency doubled by a crystal that then provides a visible, a very, very bright green laser flash that gives us the Raman spectra. And you can see that as I toggle back and forth in these images, brilliant green, and that excites atoms. It doesn't blow up the surface like the LIBS does. It excites or tickles the molecules on the surface, giving them vibrations that return photons at a different wavelength than the green laser light. And by blocking out the return laser light, we can look at those photon peaks and get some of the mineral compositions. So we have those techniques in SuperCam. The other techniques or instruments on the Perseverance rover include another set of stereo cameras called Mastcam Z for zoom, a subsurface radar instrument that's contributed by the Norwegian Defense Ministry. MOXIE is a oxygen production plant that is really showing that we could produce oxygen on Mars from the carbon dioxide with a catalyst bed, and that's what astronauts would have to use when they go there. And then there's two instruments on the arm, one called Sherlock, which I'm also involved with that science team, and then Pixel, which is a X-ray spectrometer. It makes an elemental composition map detail that I'll show you later. Sherlock is looking for organic materials in a very close-up sense. And then there's a weather station as well. So, but the really important part of this mission is a sample cache system labeled down here, and it fulfills a major goal to collect samples for return to Earth. And so I'll be talking about how we're collecting samples, dropping them on the ground and leaving them for a future mission, but we're drilling them out of the rocks as we go along and finding the best samples to bring back. So the landing location for Perseverance is Jezero Crater. It's up at 17 degrees north latitude, and it's right on the edge of this very large Isidis basin that's on the edge of what may have been a northern ocean on Mars. The colors in this map are elevation, and so the blue is not water, obviously, it's just low elevation. And Jezero Crater is right on the edge of that. You also see a very interesting feature here. This part here called Syrtis Major looks like it could be one large volcanic edifice. You can see sort of fissures and volcanic rivers that are frozen in the lava that are heading downhill off of this area here. So a very interesting area with very different chemistry, a lot of iron and magnesium in this region, in certain geologic terrains. So we went to this Jezero crater because it also has evidence of being an ancient lake with both inlet valleys and an outlet valley. It's about the size of Lake Tahoe, if you want to compare it with a lake on Earth. But it has this very beautiful deltaic formation sitting here. And you can see meanders that are frozen in the sediments that are left from the riverbed that was depositing all of these sediments into the lake over a period of time. And so if we wanted to go and look for a place where we could find sediments, basically a place that could have brought nutrients in for any forms of life, this might be a place to look. And so this is where the rover went. The other thing is that we could see from orbit the signature of clay minerals in the form of smectite, which is a type of clay mineral, as you might expect in a delta formation. We also have olivine that is down in the bottom of the crater that could have indicated a volcanic unit or just material that flowed down from the river that's from a volcanic unit. And then we have this, what looks like almost a bathtub ring of carbonates. And carbonates are relatively rare on Mars, even though it has a carbon dioxide atmosphere. And that's a real enduring mystery, why Mars doesn't have more carbonate rocks with a carbon dioxide atmosphere. And so that's another reason to come to this location. So it seemed like, and the other thing is, if we found an igneous terrain here, we could collect samples that would give us a great place and a great way to do radiometric dating if we brought those samples back to Earth. And if we have, the main way that we study or understand the ages of the surfaces on Mars now is through counting the density of craters. And so if we could calibrate the crater counting ages with radiometric ages, we would learn a lot more about the timescales of Mars. And so that's another goal of this mission. So here's a video. I think there is sound with it, and if not, I'll try to unmute my sound of the entry and landing. Yep, I hear the sound. I hope you can too. So it took 9 months to get to Mars. This capsule is as large as the Apollo capsules that brought people to the moon. And it has to slow down from 11 kilometers per second.
Indicate chute deployed.
The parachute deploys.
The navigation has confirmed that the parachute has deployed.
And that was a supersonic deployment, which is really tough. And then the retro rockets have to slow it down. And the neat thing is we actually have video right here that is brought back later from
maneuver has started.
this landing.
About 20 meters off the surface.
And here's the animation again. But for the first time,
Ready to begin seeking the sands of past life.
so this is the first time that we actually got video of the landing itself, taken by that jetpack that lowered the rover to the ground on ropes, and also looking up at that jetpack from the rover itself. Really great to see. Anyway, the landing was here in Jezero crater as expected. And this is a picture that was snapped from orbit by the Mars Reconnaissance Orbiter. And you can see this beautiful delta formation. In this picture, you could actually see that the mission is actually going a little bit past the delta formation. We were hoping to land right next to it, but we had a larger landing ellipse, we knew. And there was a feature called terrain relative navigation. This is a parachute and capsule, by the way, in that picture. And that navigation with that jetpack was designed with images that were already installed in the computer to show it where the safe landing places are and where the cliffs were. And it was designed to avoid the cliffs and land in the smooth areas. And so it did that. We landed right there where the star is, and it avoided a rough spot that was just to the left of that. And I'll show you that. It found a very small, smooth landing spot to land. You can see that right here. Perseverance landed here in a very small, smooth spot around all of this rough area to the south and to the west of there, and to the east for that matter as well. And so we're very grateful for that safe landing. I never trust NASA with its landings. This is my third NASA landing, and the first one was an utter failure with the Genesis mission. Since it was on Earth, we actually still got our science back, and that's another God story. But the two landings on Mars were very fortunately successful. One of the first things that we did in the first 3 months of the mission was to deploy Ingenuity, the helicopter. And this helicopter is amazing because of that thin atmosphere on Mars. And so the blades spin such that the edges of the blades are going just about at the speed of sound. You couldn't really go supersonic with a helicopter, or that would not work. And so this is right at the edge of the envelope of feasibility. And yet it is, and this helicopter was just made to be a small demo, yet it's still actually operating. It made another flight within the last week, and the neat thing is it survived the Martian winter. It doesn't have the mass to self-heat itself. During the mission itself, it can, or during the main part of the year, it can keep itself warm at night, but during the Martian winter, it browned out every night, and yet it woke up every morning and still was able to recover and fly. So that's amazing. In terms of the science, we trained our images, our cameras on this feature almost right away, which is a delta remnant. That is, much of the delta eroded back over time, but this is a harder part of the delta, and so this butte remained. And the neat feature is that we could look at this with our cameras and see the layers as they were laid down as the lake was developing this delta formation. And the way it works, if you ever talk to a sedimentologist, if you're in the deep part of a lake, you get very fine material that settles out as silt out of the lake. But then as you're near the edge, and especially where a river empties into a body of water, there is delta. If there is a lot of sediments upstream, the delta is actively forming, and you will continually get more slanted layers deposited along the slopes. They're called foresets in the rock record. And then once that delta is there, you may still deposit a little bit of rock as if your lake level rises, and those are called top sets. And we could see all of those in these very beautiful rock layers that we could look at with our cameras already. So very, very clear evidence that this was a rather deep lake. We could actually tell the depth of the lake and look at how the delta itself was being formed. Just beautiful. People were just so excited to see that. This shows the traverse of the rover in our first 2 years. It also shows where the rover and the helicopter are now near the delta formation. But just for a minute, I'm going to focus on the early part of the mission. We landed right here, and whoops, I hit the button already. So as we traverse down to the south and into this area, this rough area called Seta, first we went through Maas Formation, which is down here, and you can see the magnesium in that volcanic reunit is very low. But then we got into Seta, and boom, the magnesium went way up in the SuperCam data, and we knew we were into a different igneous rock terrain. And so people actually, I mean, the kicker is that we were possibly expecting sedimentary rocks here, but we found igneous rocks. And so, so there were volcanic rocks that occurred at some point, maybe before part of the lake. So this is a picture from SuperCam looking at some of the mineral grains or crystals in this very magnesium-rich rock. And it turns out it's very much like some ancient rocks on Earth, where we have a lot of olivine crystals. And so very interesting to see some relationships to what we have for ancient rocks, where it's called an olivine cumulate. Must have been a quite thick layer of igneous material, because these crystals are thick or quite large, a couple of millimeters in size. That indicates that they cooled quite slowly, but there's disequilibrium. These crystals actually were in a larger magma chamber, and they started to crystallize, and they're denser than the rest of the magma, and they settled to the bottom. And that's why you see such a strong concentration of olivine crystals all together here, and a very high concentration of magnesium. It's not characteristic of the magma or lava altogether. We had some discussions whether this was some avalanche of coarse-grained material down into the lake, or whether this was actually an igneous formation. But this view from the pixel instrument shows, and these are element maps, shows that the mineral grains themselves are interlocking. They're grown inside of one another, and that's primary evidence that they actually crystallized together, not some kind of avalanche of small grain material. And on the right is a Martian meteorite showing a very similar kind of formation. So after that, we drove the rover last April over to the Delta front and started exploring this sedimentary region here. We explored two different regions, one around what's called Hogwallow Flats, and in one near what we call Enchanted Lake. This was a rover location at one time. And then we actually dropped off some of the samples over here at Three Forks in a very flat area that will make a nice potential landing site for the sample return mission. And so we had some beautiful views of the edge of the delta. You can see this beautiful layered material in sort of mudstone, which is a fine-grained sedimentary rock, or sandstone. And so that makes up the slopes of the delta. It was very interesting to see. We found more magnesium-rich rocks there. We drilled some samples, which I'll talk about in just a minute. And when we do that, we also make an abrasion patch, which means we can look a little bit beyond or below the surface of the rocks to get the best picture of their composition. This is a picture of the first drill sample that we collected. And so that's part of the sampling that we do. This is a montage of all of the different samples that we collected. You can see some real coarse-grained rocks from the floor of the crater there. And these are igneous rocks down here from the floor of the crater, and then sedimentary rocks from the delta front. And so this is another picture of where we set off to drop off some of those samples. In many cases, we did what we call double sampling. So we collected two samples from the same rock, just like you saw in that picture. And the idea is to drop off some of the samples here as a contingency place for the sample return mission. But we want to drive on with the rover farther and collect more samples, and maybe we'll meet that sample return mission in a different place with a lot more samples to give them. But in the meantime, just in case something bad happens to the rover, we drop these samples off as a contingency, and this is the location where they are in an overhead view, and the names of these samples. And so this is where the return mission could pick them up. If the rover dies or something else fails, this is where we can go with that sample return mission. Very nice flat spot. There's a picture of one of those sample tubes dropped off on the ground. This is a short video just showing you how the sampling happens. And little animation showing the drill core being brought into the rover here, into the what's called the SCS, or sample cache system, through this turret that spins that down into a vertical position. And then there's another small arm down below in this cache system that picks that up, brings it to a imaging station, a capping station, and then and brings it over to a storage area. And the storage area is here on the left. And that's where the tubes all sit. There's room for 43 of them. And then when it's time to drop them on the ground, it just releases them onto the ground. And the next mission will have the job of picking them up and putting them into the nose cone of a rocket that will be brought to the surface of Mars. So this is what it looks like, or what they think it will look like. All of the details are still being worked out for this mission that is supposed to go around 2030. have a small rocket that's about 7 feet tall. I think it's 2 stages. Get it into a very low Mars orbit where the sample container, it's called the orbiting sample, or OS, will then be picked up by another spacecraft that will ferry it out of low Mars orbit and back towards Earth. And it'll insert it in a capsule that will then survive the entry of Earth's atmosphere and bring it down into the Earth. I wanted to leave just a little bit of time at the end of this to talk about some things where I've seen the evidence of God in the way that I've worked in my projects. First of all, this is a book that I wrote at the landing time of Curiosity that gives a few of these stories. It was published with a secular publisher, but I still talk about times when I really prayed for this mission, actually when my boys prayed for it as well with us. And but the spiritual background of this is that I really felt so privileged to be leading this mission. I just felt like it was something that God gave me to do as part of my mission in life. But there was a time when NASA actually came and canceled ChemCam. It was a time when we were about this far along. This is the engineering model of ChemCam, and we were already building the flight model. And what happened was the rover itself was over budget by about $75 million. And the associate administrator of NASA was very upset with this kind of overrun. Felt like he had to have a scapegoat. There were several instruments that were a fair amount over budget. There were 2 NASA center instruments. Each one was about $20 million over. Our instrument was about $500,000 over. But NASA needed a scapegoat, like I said, and they didn't want to look to their own people for that. And they ended up announcing the cancellation of ChemCam. So here I was leading this great instrument with an international team, and this cancellation was announced. And so it was like the bottom fell out underneath me. I just knew that God was in control, but it was like, why would this happen? It turns out that I've really benefited from this cancellation, which, as you must know, did get turned around. But it was so needed by me just to say, you will have no other God before me, Roger. This is your maybe the child of promise, kind of like Abraham with sacrificing Isaac. But you are going to bring this to the altar. And so I did. I said, you can do whatever you want with this, God. And it came back in a miraculous way. The associate administrator was actually bad-mouthing our institution, even though we were not the cause of the overruns for this mission. And it started a chain of media misinformation. There wasn't anything we could really do about it at the time. But this administrator was actually fired within a few months, and then we were able to turn things around. And I write about that in the book. And it was, like I said, a huge answer to prayer, but also just a show of who was really in charge. And so ever from that time on, I know very much that whatever successes we have, it's not to my credit. It's really God who sets people up and demotes them as well. As Joseph said to his brothers, actually, in Egypt as well. There was another time that I wanted to, so I have this picture of myself leading worship in our church at that time. And I could say really that tears were coming down my cheeks as I was playing the piano and singing these songs. So this was, I wanted to share this. This was when I received an award afterwards. And this was part of my team gathered here, and I have the pin on my lapel. But I'm giving this talk and just saying, it was really a miracle, and I thank God for bringing ChemCam to fruition, and we've done a lot of successful things with it. But there was a big burly guy from NASA in the audience who was also invited, of course. But I think he was perhaps the one of the main people behind kind of throwing us under the bus, letting us get canceled. And as the party wound down and it was time for people to leave, he came to me and shook my hand, congratulated me again. But he looks me in the eye and he just said, "ChemCam really was a miracle, Roger." And you know, it's great to give God the credit in times like this. There's one other thing, and I'll make this brief, but it's kind of a Romans 8:28 time for the SuperCam mission. We were 3 or 4 months from delivering this instrument to the rover. This is a binational thing, and the French were developing this part with the laser and the telescope, and they had to deliver it to us in about 2 months. They were just putting the last little bits of glue and staking some wires in place, put it in a thermal chamber to dry that out and heat that up a little bit. And a terrible accident happened. And they came back to this chamber where it was drying out, and it was too hot to touch. This thing had gone into runaway thermal mode, and it had melted the solder on this instrument and just completely destroyed it. And I got a call with people weeping from France. But this, and I was on a plane almost right away to go over and try to figure out what we were going to do. But it went right to the top of NASA and the French Space Agency right away, with people vowing that we would get this on the rover, which they did eventually. But the story behind it that I want to say is that right before this happened, there was a test of the instrument trying to see how it would do at the cold temperatures of Mars. And this test showed, very unfortunately, that the telescope was defocusing when it got cold, and we could not focus the telescope. It had a flaw, sort of like the Hubble telescope, and we did not know what was causing this. Because of this failure and the need to spend time to pull together the spare parts and all of that, we had time to, you know, of course it was the midnight to 1 a.m. time, but we did have time to think about this test and what was causing the mirror to deform. And we figured it out, and were able to order a mirror that would not deform at cold temperatures and install it in this instrument in the same time that they were assembling all of the spare parts to make the second one. And the second one was assembled in record time with 2 shifts, 6 or 7 days a week. We skipped some of the calibration, got it straight to the rover, and it worked. And we didn't know how well that telescope and camera worked until we got it on the surface of Mars, because we couldn't take any pictures outside of the clean room. And so the first pictures that we snapped at Infinity was actually this one here. This is part of the Delta front that we took on day 26 in Jezero Crater. And so when we got this picture back, our jaws just dropped, because this picture has much better resolution than ChemCam, which was supposed to be the same design. And in fact, Mastcam Z, which snaps the pictures for most of the pictures for the rover and has this picture in the bottom, was supposed to have better resolution than SuperCam. But when we look at these, this is the Mastcam Z version of these rocks in the Delta, and this is the SuperCam image of the same thing. And you can just see how much better resolution. You can see all the ridges and the rocks. You can see the small little rocks and so on. This is 1.5 miles away, and we can see rocks the size of a softball in this picture. We're never supposed to have that kind of resolution, but it was thanks to this hardship that we had in the last several months before delivery that caused me a loss of a lot of sleep and a lot of other people. And at the time I was asking God, why did you do this? This is such a crazy thing, and we're having trouble surviving this. And will we even make it to the rover? So I thank God for giving us the hard times it really, all things are working together for good to those who love God. So I want to thank you for listening to this presentation. I'll leave you with one clip with Matt Damon and the ChemCam.
Hey, Johansson, I know you don't like it when I touch the ChemCam, but I'm touching the ChemCam. a lot.
That's an outtake from the movie The Martian. So thanks for your attention, and I'm very glad to be with you, and I'll take questions.
I'll ask one. Roger, how do you distinguish the olivine and the pyroxenes? Because do you have any X-ray, or is it primarily just composition?
Yeah, I mean, it's composition, and we have actually multiple ways. So it's a nice question, because the olivine gives us a double peaks around the 820 to 850 wave numbers in the Raman spectrum. And so we can see the actual mineral vibration bands of olivine there. In the elemental composition, we see iron and magnesium in a proportion with silicon that is higher than you would get in a pyroxene. A pyroxene is a 2-to-2 sort of ratio with iron and magnesium, whereas olivine is a 2-to-1 ratio with silicon. So we have the lower silicon in the olivines as well than we would with a pyroxene.
So the mineral detection crystallography is from Raman spectra.
Yes, but also the infrared, and in the visible and infrared range, we have a very strong dip around 1 micron as well. So we actually had 3 techniques that were telling us this was olivine, all within the SuperCam instrument. So that's pretty exciting for us. Thanks, Ken, from a true geologist. And I'll answer Doug's question if
Yeah, go ahead and answer Doug's question.
Yeah. So the chat says, I see you're unmuted, so go ahead, Doug.
Well, okay. I just thought since I'm here, I might as well ask it verbally since it's part of the deal here. I just was thinking, gosh, those sample tubes aren't big. I mean, they're the size, I think, of maybe a little larger than a test tube. And how are they going to find them? I mean, I'm just thinking, if I were in the Arizona desert and throwing a test tube on the ground, I would have a hard time finding it later. And you're going to go to another planet and find these things? I obviously somebody thought about that. I'm just wondering what the thinking is.
Yeah. Well, you saw some of the imaging that we have, both from satellite and from on the ground. And I think with both of those, we know the exact location to within, say, 2 inches, or maybe something like that, to where these are on the ground. Some people ask also, are they going to blow in the wind or something like that? The wind seems quite successful at blowing sand and dust particles, but that thin atmosphere just doesn't have much power to it, so it cannot blow structures around like it did in the movie The Martian. So those things are going to just stay there. They could get a little bit covered by or have maybe a sand wedge behind them in the wind, but they'll be fine. They'll be right there, and we'll be able to grab them, no problem.
Yeah, amazing achievement. And yeah, getting buried in the dust accumulating over time is another thought too that I guess you guys must have had to work through. But amazing achievement. Congratulations.
Yeah, thanks.
I have a follow-up question to Doug's, and that is, what kind of timeline is envisioned for collecting them? And actually, I have one more question. You mentioned that I believe there are 43 locations for the containers. So what if more than 43 are collected? Or is 43 then the tops that can be collected?
Yeah. Remind me of your name, please.
Oh, I'm Sabina, and I'm Kirk's wife, and we met Sabina. Yeah, we met at ASA a couple of times. Yeah.
Great. Yes, I remember, but I couldn't remember your name. And that's just
Kirk. Oh, you need to change
it.
Yeah.
Oh, it just says Kirk. I got to fix that.
Yeah.
Thanks, Sabina.
Yes.
Good to see you again.
Thank you.
So, and your question was, now I'm trying to remember because I got.
The first part is sort of the timeline that's envisioned for collecting them. And secondly, is 43 the limit that can be collected?
Yeah.
Or how will that be handled?
Yeah, I believe NASA is going for a 2028 launch of the sample return material, but it's going to take several years to implement. And so I think we're planning to get them back in the time frame of about 2031 to 2033. So we'll just see how things go. And so that's the way it's going to work. And sorry, and then I forgot your second question.
Sure, no problem. And it's later for
It's
you
late in Indiana.
also. Yeah, and you've been sharing things deep in your heart. So the other question is just, is there a limit to how many samples can be collected and preserved?
Yeah, the samples, we have 43 sample tubes, and so we cannot collect more than that. The return mission, I do not think its requirement is to hold that many samples. And you can see, in fact, already we dropped 11 tubes in this contingency area. So we've already gotten rid of, we only have 32 samples left with the rover. So the maximum that we could ever have would be 32 at this point if we collected all of the ones from the rover. But there's some size constraints to the capsule and all of that. It's really quite a constrained mission to get these things back to Earth. Yeah, and that's partly why those samples are really quite small.
And so after the 43 samples are collected, that's it?
Yeah, that's right. That's all we can do. Now the rover can continue exploring, and we're learning a lot about Mars from all of our science that we're collecting with the instruments. But for the samples coming back, that's it for those.
So do the rovers just continue going as long as they've got power and as long as they don't break down, and then they just die on Mars? Is that kind of the game plan?
That's right. There's no EMT to bring them back to Earth.
Right.
The end of the mission.
Couldn't the Martian go back and just take extra sample tubes? And that's a joke, of course.
Oh, I'm not sure.
Well, yeah, right. So, I mean, even with the movie The Martian, they left a lot of hardware on the ground there, and just were able to get the astronauts back. So, yeah, all of the old rovers are still sitting there on Mars. We now have a few junker vehicles on Mars, you could say. But yeah, I mean, this rover could last potentially for 15 years. NASA always puts a sort of nominal mission, and that's so that we make sure that all of the hardware lasts at least that long. We have to test it to 3 times that lifetime, but in reality, a lot of things last a lot longer than that. So the nominal mission is actually over as of this month for the Perseverance rover, but we're expecting that it'll last another 10 years.
How about Curiosity? Is it still going?
It is, yes. And so its mission lifetime was also 2 years nominally, and it is still going. Part of
It's
the
been 10 years, right?
Yeah, 10 years. Part of the limitations on that is the power. And of course, the other things is whether the mechanisms will break down somewhat.
And so did you say that they're nuclear powered?
Yes, and so there is a plutonium-238, which is powering these 2 rovers. Plutonium-238 has a half-life of 88 years, but it's put into a power pack where we are generating electricity in a solid state manner, about 100 watts currently for Perseverance. And that's going down by about 3 or 4% per year due to corrosion that happens at this junction that actually produces the electricity. And so that limits the lifetime. Curiosity now is putting out, I think, something like 80 watts instead of the 110 to 120 that it started with. So it's getting down there, and eventually it won't be able to keep itself warm overnight and a few other things. And at that point, its life will get really short.
Hey, Roger, this is Kerry Aruas, the Fresno chapter RTB, and back in 2012, I gave a little award to the Mars Science Lab team down there at JPL. I don't know, don't remember if you were in the room or not, but I, being a soil scientist and all, when you started talking about magnesium carbonate and not much calcium carbonate, I was wondering if you, how many of the serpentine type rocks have you run into is basically what I wanted to ask.
Yeah, so I showed this olivine, these
Yep.
olivine crystals, and we do see some alteration to serpentine, which is a weathering process that happens with olivines. It happens fairly rapidly on Earth. The dark green beaches on Hawaii are really pretty young, and they get weathered away quite fast. Yeah, so we saw some serpentine, but it looked like it was just a small amount of alteration in the minerals that we were seeing. We may be seeing more of that at the Delta. And so we're trying to quantify that a little bit better. Yeah, so that's a process that's happening. And then also some carbonation that we're starting to see, some production of magnesium and iron carbonates as well from that original olivine.
Well, Curiosity is our honorary soil scientist, so I'm really glad to see she's still kicking it.
Yeah.
Thank you.
So I have to say that the pictures of the layering, the sedimentary layering, it was just, I had no idea that anything like that could possibly exist on Mars. Is there a theory? Were those layers laid down by water?
Can't hear you at the
wind,
moment,
or
Kirby.
what?
Mind saying the last two
you-
sentences? We couldn't hear you.
You blanked out there for a bit.
I did. Oh,
You did,
okay.
at
I'm
least
sorry.
for us, you did.
Yeah, I think it was your problem, Kirk.
Okay.
Oh, all right. Okay,
Yeah.
it was us.
Sorry.
Never mind.
So
Sorry.
did you hear me, Roger?
Yeah, so you're asking, how the layering basically happened and how it was preserved, I guess.
Yes.
And so we have the two scenarios, both with water. In Gale Crater, we had layer upon layer of basically millimeter size or millimeter thick layers, and those were fine grained materials at the bottom of a lake. And so that was just mud accumulating in layers, and then there must have been overpressure, a fair amount of overpressure to lithify, that is to solidify and harden those layers over time. And we don't know if that was some big ice field that was sitting on top of that, or many meters of many feet of rock that were on top of that. We're not exactly sure. We think that there was probably a thick overburden at one time, and then it got more excavated by the wind over time on Mars. And then
we're talking probably hundreds of millions of years. Is that right? Or that is for these sedimentary processes where we're I mean, maybe 10 times as much as we see on Earth, I would think. Is that
it's hard,
or more than that, maybe even?
Yeah, it's hard to put a time scale on that when you get over a fairly long time frame. I mean, it could have been a million years or something like that, but we expect that it was probably a lot longer. We just can't. Scientific part of me hesitates to say a number because we don't know for sure.
Right.
Yeah, I mean, there's suggestions that it was long time frames. And then, of course, a similar thing with Jezero Crater, there must have been some overburden on that. But some of those rocks on the delta front look fairly friable, so maybe it wasn't a real deep overburden on that.
Well, I'm not going to burden you with more questions if there aren't any more. I know it's getting fairly late for you back there in Lafayette, Indiana. So, but I will give people one last chance to ask their questions of Roger.
Yes, hello. This is Marina.
Hi.
Yes. Thank you, Roger, for a great presentation. I wanted to ask you if you can repeat again the discoveries pertaining to life that have been found on Mars.
Yeah. The curiosity, well, first of all, in some meteorites that are from Mars, some people found some organic material already 20 years ago. And some people thought this was evidence of ancient life on Mars, but there were some very small carbon-rich structures that actually had this, sort of almost bug-like shape. But they were so small that they were a factor of 10 too small to be bacteria on Earth, actually, or even virus cells. So small under a very high magnification scanning microscope, electron microscope. But so that was strongly doubted by the scientific community. And then in the recent rovers, Curiosity did discover organic materials. These organic materials simply mean that you have carbon chains of molecules with oxygen and hydrogen and nitrogen on them. They found carbon long chain molecules as long as 10 or longer carbons. And this is, of course, what we need for more complex molecules, whether it be proteins or amino acids or things like that. But this is right near the surface where it gets pummeled by radiation, and it's been under the radiation for a long time. And so we suspect that even if there were more complex molecules, they've gotten kind of ripped apart over time by all of the radiation. And so the question is, could we ever work backwards from the molecules we're seeing to what they might have been in the past, before the radiation kind of did its number on them? And so that's kind of an ongoing laboratory kind of process to try to understand. But that's something where we also want to understand it with the samples that will be brought back. We think that with the Perseverance rover, the Sherlock instrument has seen some organic materials as well, although there are some other possible explanations for the signals that they've seen. So we think there are some organic materials at low abundances in these sediments. But the question is where they came from. There is a hypothesis by a person, Andrew Steele, in some recent papers, where he's been looking at the boundary of carbonate and some rock minerals that are non-silicate materials, and seeing what he thinks is the production of organic molecules at that boundary in a non-biological production of organic molecules there. And I'm very glad for scientists who are looking at all angles to find the truth, and they're not just looking for life, they're looking for the processes, whatever they are. And so there may be a perfectly good non-biological explanation for organic molecules that we find on Mars, and we're trying to get to the bottom of those questions. And so that's where we're at currently.
Does the
Roger,
fact?
Thank
Go ahead. Kirk, were you going to ask a question?
Yeah, I was. I was going to say, Roger, you mentioned a Chinese rover. Can you say anything more about that? What's the timeline and where, what kind of terrain is it planned to land in, and what sort of complementary information do we expect to get from it?
And will information be shared?
Yeah, so this is the Zhurong rover. The mission's name was Tianwen-1, but the rover is called Zhurong, and it had a number of instruments on it. It landed the same year as Perseverance, just a few months later. China does not have the same kind of orbital assets and long-term Mars exploration that the US has had. And so we have 3 to 4 satellites that actually participate in getting data back to the ground from the surface of Mars. It's a relay satellites. China has, they sent an orbiting satellite along with the rover, so they have a relay, but the data pipeline, as we call it, is very small compared to what we have for the NASA rover. So they have a very low data rate from that rover. It is a solar powered rover, so it's more like the class of rovers that that NASA sent in the early 2000s. But they have several instruments on it. The other thing is that they didn't have precision landing. like NASA has had. And so they had to go to a fairly flat, kind of what I call a very large parking lot on Mars, many miles across. And with that, you don't have the sort of spectacular geological features that NASA has been blessed with its rovers. And because of that, then it's got a more sort of flat, soil-rich terrain to explore. But it's been able to drive around. It's been able to look at some small rocks in its terrain, in its traverse area. And it's got an instrument like ChemCam. It has an infrared spectrometer. It has cameras. It has a radar to sound the subsurface, and I think one or two other instruments. So it's been getting some interesting science from a more northerly point, relatively flat terrain.
Thanks.
And China is catching up with space exploration quite rapidly. So they have plans for a sample return from Mars too. We'll just see how that goes in the upcoming years.
I had a follow-up question to the one that Sabina was asking about radiation, and particularly ultraviolet. I mean, of course, we have the ozone layer here on Earth to protect us from ultraviolet, but is Mars far enough away so that ultraviolet is not that much of a problem for them?
Oh, yes, it is. It's, I mean, Earth would have a huge problem with ultraviolet radiation if we didn't have our ozone layer that is protecting us here on Earth. And so all of the surface of Mars is bathed in ultraviolet. So yeah, the very surface, of course, there you get an inch or a half an inch below the surface, and that ultraviolet doesn't get that far down. But then you have cosmic rays and other kinds of radiation that get there. So really, to get to a pristine area, you need to get about 3 feet down. I think personally that a wonderful place to explore at some point in the future, and perhaps the kind of place that astronauts would end up having to go survive in, would be some lava tube caves on Mars. And that would be really fun to explore in a cave on Mars, but we'll have to see where NASA goes with some of these things. Another way to do it very easily now is to go to a very small meteor crater, because the side of, if that was a recent crater, then the edge of that crater would be, or parts of that wall of that crater would not have been exposed to radiation nearly as much as the rest of the surface if it's a recent crater. So yeah.
Well, I think we need to excuse you, Roger. I thank you very much for an excellent presentation, and I'm sure everybody agrees with me.
Well, thank you so much. It's been
Could I ask you to close our meeting with a word of prayer?
I will, yeah.
Thank you.
Thank you, Lord. Thank you, our God, the creator of the universe, or as the Jewish prayer says, the King of the universe, who has made these wonders that we can explore, and who lastly has made us humans, who we can not only explore your creation, but also know you. And so I just praise you for how you have made us, as it says in Psalms, fearfully and wonderfully. And so we praise you over this time that we can speak together to encourage each other in the faith and to talk about your wonders. I pray for each person who's been here, that you would bless them, that you would give them your power to live their lives and to speak of you and to continue praising you in their lives actively, as well as to each other in word and as well as deed. We just pray that in the name of Jesus. Amen.
Amen. And again, thank you so much.
Thank you, Roger.
I'm going to stop the recording now.